Our second lesson from this unit on applications of integration. So basically, to this point, our work has looked at finding the area under a curve, which we did in Unit 5. Then in the first lesson of this unit, we looked at finding the area between two curves. And so today we're going to go another step into looking at if we took that area that is under the curve and revolved it or rotated it around one of our axes, we would create a shape. All right. And this is called a solid of revolution. And we're going to talk about different ways that we can find the volume of that solid. So again, I know it feels like we're kind of making a big leap here, but ultimately, this is going to always boil down to finding and evaluating a definite integral. So something you've been practicing for a while now. Okay, so let's look at this example first. So if you look here, kind of like this is what we would have looked at in our last unit, right? That's the area under the curve, that quadratic, between 1 and 4, all right? And if you took that and you rotated it around the x-axis, right? So if you revolved it, you would create this solid of revolution that you can see in these next views, okay? And how we're going to do this, how we're going to find the volume of this, is we're going to find the area of like a subsection of this, right? So by slicing it into tiny sections, we can find the volume of one of them and then find the volume of all of them and add them together. All right, so let me show you how we're going to do that. Okay, so I'm going to do the integral. Actually, first, I'm going to find the area of one of these subsections. Okay, and the area of one of these subsections, all right, if you look here, the area of one of these is going to be a circle, right? So if I were to slice, like this piece right here, right, and you turned it, you would see that that's a circle. And you guys know that the area for a circle is pi r squared, okay? And if you look here, the radius of this circle, I'll just use the one that I drew here. The radius is the distance from the center of the circle, so the center, to any point. And you notice I drew it to the point that is actually a part of our function. So our radius for this one ends up being our function. So I'm going to write down that our area is actually pi times our function squared. And our function is x squared minus 4x plus 5. All right? And all that squared. So once I find this, right, I'm going to find the integral, right, because I want to find the volume. So I have to go backwards to find the volume when I have the area. I'm going to find the integral of that area between 1 and 4. I believe it's 1 and 4. Yes. Between 1 and 4 of pi times my area function. Okay? So essentially what I'm saying is that I'm going to need to multiply out x squared minus 4x plus 5. I'm going to expand that when it's squared. Okay, so what I'm going to do is I'm going to expand that x squared minus 4x plus 5. Let me put this first. So the integral is going to be integral of 1 to 4 of our area function, which I know pi is going to be part of it. But now I'm going to do a little side work here. I think I have an extra slide. Yes. I'm going to do a little side work here and do x squared minus 4x plus 5. And I'm going to do it twice. All right, so I'm going to do this twice. It's going to be x to the 4th power. Then I have minus 4x cubed plus 5x squared, okay? Minus 4x cubed plus 16x squared minus 20x. And then finally, plus 5x squared minus 20x plus 25. So all of that, if you add straight down, is x to the 4th power minus 8x cubed plus, what is this, 26 x squared minus 40x plus 25. So that is going to go next to, or I guess I should say, next to pi in my integral here. So it's going to be, I'm going to put the pi out front, it's just a constant. So the integral of x to the 4th power minus 8x cubed plus 26x squared minus 40x plus 25. Okay? Now, we've done many integrals of polynomials, so hopefully you feel confident about this. So the antiderivative is going to be 1/5 x to the 5th power minus, this is going to be x to the 4th power. 4 times 2 gives you 8. This is going to be x to the 3rd power. And let's see, I need 26 to be this one, right? Plus 26 thirds. Then I have x squared, so minus 20. X squared would give me the 40x plus 25x. I'm going to evaluate this at 4 and 1. Don't forget, I will multiply all of this times pi when I'm all done. All right, so now I'm going to go to Desmos to find whatever that is. Okay. So I'm going to do evaluate this for 4 and for 1. Okay. So we have 1/5 times 4 to the 5th power minus 2 times 4 to the 4th power plus 26 thirds times 4 to the 3rd power minus 20 times 4 squared and plus 5.4. Okay, but here it is as a fraction or as a decimal, your choice. I'm going to copy this and do the same thing, but I'm going to plug in 1. So where it says 4, I'm going to change to be 1. This will save me some time having to type it all in again. All right, so I'm going to write down this fraction as well. And so the first one was 412 over 15, and this is 178 over 15. So 412 over 15. So 412 over 15 minus 178 over 15. All right, so if I do that subtraction, and you can keep using decimals to help if you need it. All right, so we have, move this to the side, 412 fifteenths minus 178 fifteenths, and you get 15.6 for that, or 78 fifths. I'm going to write it as the fraction, 78 fifths, and I'm going to put that pi in my answer. So the volume is 78 pi over 5 cubic units, so units cubed. All right, so there we go for the first one. We have 78 fifths. All right, don't forget to put the pi in there. All right, so that's it for the first one. That is finding a solid of revolution. This is called slicing because if you go back to what I did here, I sliced just a piece of it to get the cross section, and I found the area of that slice, that subsection, was the area of a circle. All right, and then I found the integral of that on my limits of integration 1 to 4. Now let me show you the difference with the DISC method. All right, and I really don't want you to think there's a whole much going on here besides the fact that when we move to the DISC method, it really is just the slicing method all over again, except now you're talking about using your function squared as opposed to worrying about like the area. All right, so if you focus on looking at the bounded area and it's being rotated around, all right, we're going to find the integral from those limits of integration a to b of pi times our function squared. Okay, so we're going to try this one. You notice the visual here, right? This visual here is something that we did last unit, finding the integral under the curve, the square root of x between 1 and 4. Now we're going to rotate that, right? Revolve it around, get a solid of revolution, and find the volume of this solid. Okay, so I'm going to do the integral from 1 to 4, yes, of pi, right? This is the volume, times my function, which is the square root of x squared dx. Now you guys know that the square root of x squared is just going to be x dx, and I'm going to put that pi in front. And the integral of x dx is going to be 1/2 x squared. I'm going to evaluate that at 4 and 1. Okay, so 1/2 times 4 squared minus 1/2 times 1 squared. So that's going to be 16 divided by 2 is 8 minus a half. All right, if I change that 8 to have a denominator of 2, I get 16 halves. 16 halves minus 1 half is 15 halves. Right, don't forget this is all going to be multiplied by pi at the end here. So I have pi times 15 halves. So I'm going to write my answer for my volume is 15 pi over 2 units cubed. Or cubic units, your choice. All right, so that's it in terms of the using the DISC method, where we have our region is bounded by x equals a number, two numbers, and the curve and the x-axis. Okay, now watch what happens when we do the same thing, but we're rotating or revolving around the y-axis. So this next one is saying, what if we were to revolve around the y-axis instead? You'll see this. The formula is very similar. We're just using our y values of integration, and you'll see when we do the review problems before we take this test that the AP exam is going to ask you, they're going to give everything to you in terms of X, and you've got to rewrite it in terms of Y. All right, so in this problem, they've given it to us, right? They've given us the function written with the letter Y, but you'll have to do a little bit of algebra when we do those problems. You'll see them in the review. Okay, so I'm going to do the integral from 0 to 4, right? Again, my Y values, all right, of my pi, this is for the volume, times my function, which is the square root of 4 minus y, and all of that squared, dy. All right, now the squaring a square root means it's just going to go away, so I'm going to pull the pi out front, and we have 4 minus y dy. So the antiderivative here would be 4y minus 1/2 y squared. Evaluate it at 4 and 0. Again, we will eventually at the end multiply this by pi. So I have 4 times 4 minus 1/2 times 4 squared. All right, and you could write the minus 0, but all that's just going to become 0. So this is just 16 minus, let's see, that's going to be 8. All right, and you know that 16 minus 8 is 8, so the answer here for this volume is 8 pi. So the volume is 8 pi units cubed. All right, so that, again, you'll see very similar work. Like I said, it'll be more complicated on the AP exam because they're going to ask you to first solve the function that they give you and solve it for the other variable. So it does take a little bit more work. Okay, let's try the washer method. All right, it's our last one. Now, the washer method, just essentially what you'll see where this came about is that it's the distance or the area between two curves rotated around. And what happens when they do this, whether it's because it's between two functions or if it's because of some other line involved, that essentially it creates a gap in your solid of revolution. So you guys, you might not know what this is, probably do, but like a washer, when I think of a washer, there's just like a little hole in the middle. So it's kind of hard to see with this view, but essentially there's just a missing kind of area or volume there. So the formula we use is this one for the washer method. Lots of similarities, but you take your kind of your quote unquote higher one in terms of your bounding function. That's your first one squared minus your lower one squared. Okay. So in this figure, when I set this up, it's the integral. The volume is the integral from 1 to 4. And I'm going to have pi there times my higher one is x. So that's going to be x squared minus, and my other one is 1 over x. Let me write this. X squared minus 1 over x squared dx. All right, I'm going to move the pi out in front. Then this is going to give me x squared minus, that's going to be 1 over x squared dx. I'm going to keep rewriting this again to be x squared minus x to the negative second power. I think it's just easier for me to integrate. So that's going to be 1/3 x cubed. And then if I add 1, right, negative 2 plus 1 is actually going to be a negative 1. All right, so it's going to be x to the negative first power. And then if I were to do the derivative or differentiate, when I do that, I would get negative 1x to the negative second power. So I actually have to put a plus sign here because I want to keep it as subtraction once I take the derivative. So this is my antiderivative evaluated at 1 and 4. Okay, so let's do that. Don't forget, we will multiply by pi at the end. So 1/3 times 4, let me write it like this so you can fit it all. 1/3 times 4 cubed plus 1/4, right? Minus 1/3 times 1 cubed plus 1/1. Okay, so now this is going to be 4 cubed is 64, so 64 thirds plus 1/4 minus, that's going to be 1/3 plus 1. All right, if you want to keep going with this in terms of, doing it by hand and with your head, I'm just going to move the decimals because I don't really want to deal with multiplying 64 times another 4, although it is 256. I can probably sort this out for you, but let's let decimals do it easier for us. So we have 64 thirds. 64 thirds plus 1/4. And that's going to be 259/12. Okay, and then I have 1/3 plus 1. That one I could do easily for you, but that's 4 thirds. All right, and when you subtract these, 259/12 minus 4 thirds, all right, you get 81/4. All right, again, I'm going to put my pi in here. So my volume is going to be 81 pi over 4 units cubed. Okay. All right. So that's it, guys. Hopefully you'll feel like once you kind of sort out which one you're doing, which method, the actual integration isn't so bad since we've been practicing for a while. And again, I'll show you kind of how the AP exam is going to do some variations on these ideas. All right. Good luck.